So in this session, we are talking about parameterization and curves, and we have three wonderful papers. So the first paper is mesh parameterization meets intrinsic triangulation. The presenter is Finnendahl.
Yes, hello. Thank you. And this is a joint work of Koray, Akalin, myself, Olga, and Marc, and it is based on a bachelor thesis of Koray written at the TU Berlin and the ETH Zurich. And before I start with the idea of our paper, I would like to build some common ground. So I will quickly explain what we mean by mesh parameterization and what intrinsic triangulations are on a very basic level. So let's start with parameterizations. In this presentation, we only consider 2D parameterizations, and we start with a continuous case. So we have a function f that maps between a surface or points on the surface and points on the Euclidean plane. And ideally, this mapping is bijective, or at least locally, and we can choose the direction of f due to the bijectivity. So theoretically, parameterization means that f maps from the parameter space to the surface, but a lot of applications map the other way around. So for this presentation, it's better to imagine that f maps from the surface to the parameter domain. And what we usually want is that parameterizations preserve the intrinsic quantities like length, angles, and areas. So we can kind of imagine that f deforms the surface by flattening it to the plane, and as long as the flatlander that lives on the surface does not recognize the deformation, we have an ideal parameterization, as no intrinsic space deformation is happening. But this is not always possible, so to find a parameterization that deforms as less as possible, we usually need some intrinsic deformation energy that gets minimized under certain boundary conditions. And there are uncountably many parameterization energies out there, but what I find very interesting is that a lot of energies do this just by looking at the Jacobian of f. So they take the best linear approximation of f and measure it by integrating it over the surface and measuring it using an energy function. And in geometry processing, we usually operate on discrete meshes. So that means that f maps from points in 3D to points in 2D, and in between we have a triangulation. And the values in between these triangles are the linear interpolated values of the corners. So this leads to a constant Jacobian over the triangle, so our integral just becomes a sum times the area of the triangle. And if we take a look on how to compute this Jacobian, we see it's very simple, as f is just an affine map between two triangles, so the Jacobian is just the linear part of it, and it can easily be calculated just by knowing the two edge vectors of both triangles. And in this formulation, we see that the Jacobian changes if we rotate the input mesh or the parameter space as the vectors change, which seems odd, as the rotation of the parameterization should not matter. So what actually a lot of energies just do is they just look at the singular values of the Jacobian, which makes the whole formulation rotation invariant. And really important for the following presentation is that we can calculate the singular values just by knowing the edge length of the two triangles, because we can reconstruct the triangles knowing just the edge lengths up to rotation and translation, but those operations are irrelevant for calculating the singular values. And sure, you can trust me that a lot of energies follow this framework, but just to prove my point, I brought some well-known energies and show you that they follow this framework. First, we have the very simple harmonic energy, also known as Dirichlet energy, which just minimizes the squared Frobenius norm of the Jacobian, which is the same as the squared Frobenius norm of the singular values. Then we have the well-known least squares conformal map, LSCM, which just subtracts the area of the resulting parameterization from the harmonic energy. This area can be written as the determinant of the Jacobian times the original area, which can also be written just using singular values. Then we have the symmetric Dirichlet energy, which avoids degenerated triangles in the parameter domain by adding the Dirichlet energy of the inverse mapping as well, which is the Frobenius norm of the inverted singular values. And last but not least, the as rigid as possible energy for parameterizations, which measures how much the Jacobian of each triangle differs from a rotation. And this can be reformulated by subtracting 1 from the singular values before taking the Frobenius norm. And there are a lot of more energies that follow this framework, and these are just some examples that we used in the paper and in this presentation. And all of these methods have different boundary conditions and are optimized in a different way, so they find a minimum within the given triangulation. And our question is there room for improvement, independent of the energy? And the answer is yes. Yeah? Although they find a minimum, they rely on a given triangulation as their discretization. But different triangulations lead to different parameterizations. Take, for example, these two parameterizations. So although we have mapped the corner vertices to the same positions, depending on which diagonal we choose, we end up with a completely different parameterization because the triangle, the linear interpolation across the triangle leads to a different parameterization. And this insight we can directly use to improve parameterizations of piecewise linear surfaces. Yeah, take, for example, this piecewise linear surface. If we discretize it using a triangulation, the diagonal at the top can be chosen arbitrarily as the top is flat. So maybe this triangle or this triangulation is better for our parameterization. Actually, the triangles or the two triangles in the front can also be triangulated differently because intrinsically they are also flat, and we can choose the other diagonal as well to use intrinsic triangles to linear interpolate the corner vertices. Yeah. These are so-called intrinsic triangulations, and they are useful for a lot of optimization techniques like Alec already presented today. And it allows us to choose a better discretization to perform calculations on meshes while still describing the same underlying surface. Yeah? And this usually better discretization is usually the intrinsic Delaunay triangulation, or refined version of it. So under all intrinsic triangulations, we usually only use that one that fulfills the Delaunay property intrinsically. But other intrinsic triangulations are possible too. And we can explore these intrinsic triangulations by flipping edges, just like we already did. Yeah? So we can continue to flip other edges, like, for example, this one, yeah? And we can discover the whole space of intrinsic triangulations, as all intrinsic triangulations are flip connected. And just to make sure that everyone gets this, yeah, these intrinsic triangles consist of multiple piecewise linear areas that bend over the surface, but they can always be put onto the plane, and we can then linear interpolate the values at the corners across the triangle. So for parameterizations, this means that we can let our parameterization piecewise linearly bend over the surface as well. Yeah, there's no reason why we can't do this. Yeah? And obviously, these two different parameterizations have different energy values. So we should be able to calculate these energies. And to do so, we need a data structure. Yeah? And to store intrinsic triangulations, there are multiple ways possible, but we take the most simple one because the most simple one is enough. Yeah? We can store an intrinsic data structure similar to an indexed phase set, but instead of a list of vertex positions and a list of triangles that reference to these vertices, we store edge lengths, and in a triangle list, we store the indices to these edge lengths. And this allows us to retrieve all intrinsic quantities like angles, areas, and lengths, yeah? Because we can just lay out the triangle, we can reconstruct it, and calculate the length and angles from there. And as we have the connectivity given by the triangulist, we can even lay out multiple triangles next to each other and retrieve lengths across triangles as well. And this directly allows us to perform a flip as well. As we know the two triangles of an edge due to the triangulist, we can lay them out next to each other, calculate the length, and then we have to obviously update this length in the edge length list, and also remove the old two triangles and update them in the triangle list as well by replacing it with the new ones. And this data structure is enough to calculate our energies. As I already showed, the singular values of a Jacobian can be calculated just by knowing the edge length of the two triangles we map to between. So we have all the ingredients to make this simple observation of our paper, which is that usually we optimize the parameterization energy just by finding the optimal mapping given a fixed triangulation. But actually, we have to consider the discretization as well. So we have two sets of variables to optimize, the mapping F and the triangulation T. And there are a lot of optimization strategies out there, but we went with the most obvious one, an alternating optimization. So we first optimize the mapping of F, and then we search for suitable triangulation. And the first optimization is just the normal parameterization. So we can assume that the normal parameterization is the input to our method. And the second optimization step is actually in discrete energy. So it is not directly clear on how to optimize it, and we also went simply with the greedy approach by searching for improving flips. We just loop over all edges and keep those that decrease our energy. And luckily, this evaluation of the new energy can be done locally, as the flip only changes two Jacobians of the neighboring triangles, and our energy was defined as the sum over all these Jacobian energies. So just to visualize this, we have an input surface, we calculate the optimal parameterization, this is our input, then we search for energy decreasing flips, and here we have to be careful, as the flips might need to be possible to be done in the parameter domain as well as in the surface domain. So for that, the four vertices need to lay in convex position, so we do not have overlapping triangles in the end. And then we continue with the first optimization again, because we might have changed the triangulation. And now we have to be careful again, because now we have to reformulate our optimization strategy to work with intrinsic triangulations instead of the normal triangulation. But this is straightforward for all the presented energies, and I will skip this for this presentation. And then we continue with that till convergence. And we see that this actually improves our energies. Here we see how the relative energy decreases for a single mesh over two iterations. So we start with a relative energy of 1 in our input parameterization, and then we perform the flipping, followed by the optimization of the vertex positions afterwards. And we see that sometimes the energy decreases a lot, and for some other energies, there seems to be no improvement at all. And we also see that after the first iteration, not much improvement is visible for some energies. But we run the experiments on 710K meshes, and they nearly all improved at least slightly. And to show this, we have these 4 histograms, where we see that depending on the energy, we have a different outcome. We see that for most meshes, we do only barely improve, but for some we improved a lot. But it's difficult to compare these histograms because the optimal energy energies that are achievable by different energies differ a lot. For the symmetric Dirichlet energy, for example, the optimal energy is above 0, while for Arab it is 0. So we might have an offset which kind of skews the relative energies. And we can also see that in the resulting parameterizations. So if we take a look at this, only 0.1% improvement of the symmetric Dirichlet energy, we can zoom in this disk-like mesh, and we see that the parameterization improved quite a lot. Yeah, so the lines are way straighter than before, although we only improved by less than 1%. And on the other hand, in this Arab energy, for example, we have a factor of 13, but the parameterization only changes, I would say, by a rotation. Yeah, and rotations should make no difference in the parameterization. So I actually don't know why this improved that much. And we can also see that on the left side, in the energy difference plot, here colored in red and blue, we see that energy decreasing and energy increasing areas seem to be close to each other. Yeah? And this is an observation we had a few times. Yeah? We see that if we flip an edge, we usually increase the energy for one triangle and decrease the energy for the other. And we only keep those that improve the overall energy, which is sometimes only a small amount. But we can see that this kind of averages the energy across the quad. Yeah. We also evaluated our flipping strategy. So we again started with the initial parameterization colored in red, and then we performed the flipping using different orders of edges to consider. So we run multiple experiments with completely different edge orders every time and end up with this distribution of output energies. So we see that we land in different local minimas. And we then compared that to a prioritizing strategy that prioritizes large energy flips, and we see that it kind of lies within the random distribution. We just went with a fixed but random order of flips because you might notice that this is a really zoomed in region of the whole plot, and the relative improvement seemed to not really differ between the random flipping order. Yeah. We also made a quite interesting observation. Sorry, not optimization. We did do a quite interesting optimization, but we also found a quite interesting observation that for harmonic and conformal energy, every edge that was flipped fulfilled the Delaunay property after the flip, which is not surprising, as both rely on the Dirichlet energy, and by Ripper's theorem, the Delaunay triangulation minimizes the Dirichlet energy independent of the function, so they should decrease the energy, but this suggests that we might use the intrinsic Delaunay triangulation for the other two energies as well, so at least as the initialization. And we found out that this is not the case. Actually, it performed way worse. Nearly all relative energies went up if we initialize it with the intrinsic Delaunay triangulation. And what I want to point out is that we even got a value above 1, so we ended up with a worse parameterization compared to the classical extrinsic parameterization. So we weren't able to come back to the initial triangulation. Yeah? So we landed in some local minima without achieving to come back to the input to have a factor of 1. Yes. Let's talk about the disadvantages. Yeah, obviously, the whole procedure has some timing overhead, as we have to search for flips and rerun the optimization of the vertex positions. So this may lead to an execution overhead that takes up to 6 times longer than doing the normal parameterization, although this highly depends on the energy and how long it takes to calculate the optimization for that energy. Symmetric Dirichlet, for example, is quite expensive to calculate. So the flipping is no real overhead. Yeah? And once we have a good parameterization, the further vertex optimization after we found some improving flips is also quite fast because we have an iterative optimization strategy and we were already pretty close to the optimal solution. So further optimization steps are running also very, very fast. On the other hand, minimizing the harmonic energy means solving a linear system of equations. And this is fast, so the flipping is quite expensive compared to that. And we also have to rerun the whole solving step every time we found a flip. So that's why we got so high relative timings for these energies. And the last disadvantage that is kind of the most important one is that it's quite cumbersome to use our intrinsic parameterizations, as although they are easy to calculate, it's difficult to use them because we need a map between the intrinsic space and the surface space. And actually, our data structure is not capable of doing so. So we need a better data structure, actually. And what other data structures usually do is they calculate the common subdivision of the intrinsic mesh and the extrinsic mesh. So they insert points and their respective mapping. And then we can use standard linear approximation of flat triangles. So in this case, we would have divided the triangle into 4 triangles. Yeah? And this sometimes leads to a lot of new vertices. Yeah? Here, for example, we had to insert 4 times more vertices to be able to visualize the parameterization. And on average, we have like 60% more vertices on average. Yeah? Plus the additional overhead to calculate this common subdivision. So to summarize, the intrinsic discretization matters, yeah, because we can improve parameterizations independent of the energy. And actually, the energy does not need to fit our singular values framework. As long as the energy is purely intrinsically defined, we can optimize it with this strategy. And although our method it works independent of the energy, the results are highly dependent on the energy. And additionally, we found that intrinsic Delaunay triangulations is not always the best way to go, and the overhead might not worth the improvement. So thank you, and I'm open to questions.
Thank you for the talk. So how do you avoid triangle inequality violations when doing the optimization? And do you do anything to avoid near degenerate triangles for numerical stability?
So we have to consider a valid flip in the parameter domain and in the surface domain. And for the surface domain, we just use the normal checks that were provided by the data structure. We used the navigating intrinsic triangulations data structure from Nick Sharp et al. And in the parameter domain, we have a flat surface, so we just need to check whether the 4 points are in convex position. So this is quite easy to do. And actually, it's not even necessary, yeah? Although it might lead to overlapping triangles if they are not in convex position. But that shouldn't be a problem of our method, but a problem of the energy. So if the energy allows for flipped triangles like ARAP, the energy should say that this configuration is bad. So we should avoid the flips using the energy. But for energies like symmetric Dirichlet, which cannot handle flip triangles, we have a problem. So that's why we always check for this constraint. And the other question was?
Do you avoid near degenerate triangles, ones that are like slivers?
No, we don't, except for if we have such cases, we usually had no real difference in the energy difference. So we flip the edge, calculate the energies, and compare it to the previous one, and there were usually a lot of numerical inaccuracies due to these slivers, and for that reason we just removed them. So we didn't have issues with that, I think.
Okay, thank you.
Thank you very much, nice talk. 2 questions. When you do the edge flip, right, so you get this geodesic edge curve on your mesh, the corresponding thing in the parameterization domain is not a straight line anymore.
It is.
Under the linear mapping.
Under the linear mapping, no.
So do you have to take that into account when you're doing the integration and the Dirichlet calculation of the integrated energy?
So in the moment of the flipping, it is straight, because that's how we calculate the energy. So in the moment when we flip, we use this as the new discretization, this flipping, and so then the line is straight in the parameter domain.
So are you forced it to be straight in the
Yes, yes, yes.
Okay, so you don't follow the image under the old map.
If we do so, I think the energy wouldn't change. But I'm not sure. Yeah?
Second question, totally unrelated. The energies that you have, if it's the Dirichlet or the conformal energy, the minimizer is unique, right? You get an intrinsic Delaunay triangulation. Can you say something in general?
Wait, I forgot to say something, or not forgot, but I leave something out. Due to the situation that we need to check whether the flip is possible in the parameterization as well, leads to certain flips that are not possible in our configuration that are possible on the surface on its own. Yeah, so these intrinsic triangulations may lead to self-loops and different configurations, and they might be necessary to reach the intrinsic Delaunay triangulation, but we cannot allow self-loops because this would lead to degenerated triangles in the parameterization. So we actually cannot explore the whole space of intrinsic triangulations, and for that reason, we don't even know if we really use the best triangulations, because we ended up with using the as intrinsic Delaunay as possible triangulation. So sorry, but still, maybe there's still a question.
I don't know. So you can tell me if there's a good. Now, I was wondering if the original work that shows without the constraints the intrinsic Delaunay triangulation is unique, sort of.
Yes, but ours isn't.
So yours is, but putting aside the question of parameterization, if you do define a different energy on triangulations, is it clear what properties it needs to satisfy so that the minimizer is unique? Can you say something about,
Oh, no, unfortunately
if you
not.
use a different Jacobi energy, is it, is it likely to have a unique minimizer?
This is the problem with discrete energies, right? So to say something about this, you need to really understand the problem, and I think we didn't look that deep into the problem, yeah. But it would be interesting, but yeah.
Any other questions? I have one question. So can you say about the boundary conditions in your parameterization? Are you fixing the boundary, or?
Yeah, we sometimes had to adapt the boundary conditions. So every energy has a different boundary condition. You might know that the conformal, the LSCM energy, has a free boundary, and this leads to different areas or resulting areas for our energy in the end. And after flipping, we end up with a different energy. So we needed to normalize some of the energies to be comparable within different iterations. But yes, I don't know if this answers the question. This was a completely different question.
I have also a follow-up question. So this going back to the flipping in parameterization. So you are mainly focused on distortion minimization. So sometimes we care about injectivity. I know you do this check, the convexity check when you do the flipping. However, the first step in your alternating optimization could still result in a flipped parameterization.
Yes, correct. And that's why we only ended up with 700 thingy 10K meshes, because we filtered those that didn't end up with.
But flip could happen during the iterations.
No.
Could it? No?
No, it cannot, because whenever we flip, we do not change any triangle layout, only. Ah, yes, sure, of course. That can happen.
And would you recover from it, or it's like you are stuck with that flip?
I think we stopped then.
Okay. Got it.
Sorry, yeah. That's,
All right, any other questions from the audience? I want to ask one more question. So in your limitation, you said like to visualize this intrinsic Delaunay or parameterization, you need to basically doing a joint refinement of your intrinsic triangulation with the extrinsic triangulation. What do you foresee? Like, what do we need to do to make intrinsic parameterization more easily usable? Because like the current ecosystem, they all rely on extrinsic triangulation.
yes, I think I think we need a nice data structure that easily maps between these two surfaces, because currently but I think in the end we have to find these points. So I don't know. I actually don't know how to improve this step to be able to use it in a practical sense. Although it might be useful to consider these new inserted vertices as real refinement steps, so we can use them as new vertices to optimize as well. So we have kind of a better guess as for Steiner vertices for our refinement. But I don't know if this really leads to better parameterizations.
All right, let's thanks speaker one more time. Thank you. So next we have a talk on distance-based smoothing of curves on surface meshes. So the talk will be given by Markus Pawellek.
Thank you very much for the introduction. I'm Markus, and I'm from the University of Jena. And so let's delve right into the idea that we have for smoothing curves and surface meshes. What is the actual problem that we're talking about here? We start with a triangular surface mesh that we see here, this standard model as we heard, and we all still use the standard models. And then we're also given an initially, let's say, jaggy surface curve on this kind of model. We're describing these curves here as edge curves. Yeah? So all segments of these curves run off the edges of the surface mesh. This is for us around the constraint. And what we want to generate out is another curve whose shape is very, very similar to the original shape and provides somewhat a relaxed or a denoised shape. This relaxing we want to define as a reduction in geodesic curvature. So this is the kind of problem that we try to address. Our motivation thereby mainly stems from the area of medical applications, but it's totally not limited to that part. Here, for example, one application, of course, segmentation is always a good thing, but we could, of course, try to apply it to the automatic segmentation of aneurysms and blood vessels, where we start off with these very jaggy surface edge corners that we don't want to have, and for medical applications, and of course also for other applications in engineering and whatever, we need a certain smoothing for the resulting curve that it actually transmits, not the discretization error of our underlying triangulation. So what are we doing? What is our algorithm? What is our idea? We start here with this example of a planar circle to try to visualize it in a little bit better fashion. And we have our surface S, and we have our initial, hopefully jagged curve, such that we can smooth it on this kind of surface. And the first thing that we want to construct is a so-called penalty potential. And this potential, bear with me, shall somehow, we will talk about this in a minute, penalize larger distances from the initial curve. Now, the most essential step right now is that we want to lift that surface. So this is the second step. We want to lift this surface by the lifting operator. We do this, we can look at this by this one here, by appending the value of the potential at a vertex to the fourth coordinate to the vertex, essentially lifting our surface into the four-dimensional Euclidean space. We have visualized this here. We now see that our planar circle has evolved into, let's say, a relief of mountains, and by the chasm we have here created, there flows something like a river. We can imagine it like that. And the idea now is that the river flows over time and straightens itself. We will not introduce time, no worries. We will introduce the straightening approach by the determination of a locally shortest geodesic that we try to generate by using this black curve that flows in the cavern as an initial gas to the local algorithm. Now, of course, we have a locally shortest geodesic that mostly reduces these geodesic curvatures, hopefully is 0. And we see also that this geodesic curve runs near the original, at least in the lifted surface. Of course, we're now in the lifted surface. The last step is the simplest one. We project now everything back to the original surface, try to remove it back. Sorry that there is no animation, but we can now see that we have a smooth surface that is relaxed and denoised and runs in a similar shape to the original. And that is the overall idea of the algorithm. There's, to be honest, really nothing more to it than this kind of smooth understanding, so in the mathematical sense, but we have to delve in a little bit into the details. So we, of course, need to somehow construct this kind of penalty potential. And to do this and being able to do this, we want to know, okay, how does this work? So we want to reformulate our algorithm, and step number 3 is exactly what we want. We can reformulate it as an optimization problem. We heard a lot about optimization problems, but determination of locally shortest geodesics can be easily described by a Dirichlet energy term that we want to minimize as an energy term. But we are also very lucky because the lifting operator xi phi that I've defined right here builds a diffeomorphism, and by using this diffeomorphism, we can easily extend this this optimization problem formulation to our whole algorithm to construct something like the following. And I'm deeply sorry about this massive equation right now, but it's not really that hard, I promise. So at first, let us look what we want to do. Of course, we want to minimize an energy term, and I told, okay, alpha will be a curve, so it's only a running variable here. And it seems to be complicated here. Gamma, gamma, S, that's only the set of all the curves with the same start and end points, or at least in the same isotropy class of the initial curve gamma in S. And we put this into our energy term. And the energy that we're constructed here is, of course, this Dirichlet part. And this is also part of the original locally shortest geodesic energy term. So that actually doesn't change. This part is there to shorten the curve, and therefore somehow, in some sense, in some, let's say, average sense, reduce geodesic curvatures. So indeed, the smoothing acts as the locally shortest geodesic acts here as the smoothing strategy. But let's take a look at the second term. This looks a little bit more complicated. Our potential comes in as the gradient, and we'll somehow multiply with the derivative of our given curve here. That is indeed at first not something that we would say, okay, does this really help? Does this really help to constrain the curve? And yes, it does when we construct the potential in the right way. Our idea is that we want values that are further away from the initial curve to provide out with larger values. And the idea is, okay, if the curve travels far away or wants to travel further away from the initial curve, it must somehow travel along the gradient of the given potential when we construct it in the right way. In this way, the second term therefore acts as this kind of shape constraint to actually fix the smooth curve a little bit more to the shape of the original curve. And looking at the second term, we also see, okay, we see nublar phi, so the gradient, and it also gives us kind of an idea how we should construct the potential, but at least we see that norm of nublar phi must take larger values for increasing distance. Not only phi, also the norm of nublar phi. And we use this information now to construct a potential. But we need to say something. Before we go into the details of constructing the potentials, there is not a unique way of constructing these potentials. You can probably find your own way, maybe a better one, maybe for other applications. We've tried to choose the most simple one and one of the most efficient, which is kind of robust in the examples that we had. So we started with a smoothed distance field. And here I say smooth distance field. You can also take the distance field in practice, of course, because we're describing everything in terms of operations on smooth manifolds. I want to make it mathematically okay. So I put the smooth term in, and we will see it's not really a problem. What we can directly deduce from this one, we heard from it in graduate school and from other presentations, is this iconality property that we have here. We know, okay, the norm of nublar delta gamma from our smooth distance field is somewhat approximate one. That's not the property that we want. So we can't use the smooth distance field itself. Therefore, we modify it with a modifier function. We build a simple composition, and we build this composition because it's easy in this case and doesn't really introduce a lot of new things. And for that, I also introduce a parameter tau. The tau parameter shall be used to, let's somehow say, find the trade-off between the similarity in shape and the smoothness. We can decide for that. How do we define that? First step is we use still another function. So I will give you through the whole process of all these things. And the first function g, we will see it in a moment, gets the arguments a, tau, and x. And the multiplication of tau in the argument of the function g, as I said, is one of the simplest ways to achieve a tolerance parameter that somehow gives you a trade-off between similarity in shape and smoothness. We define the parameter a to be 10. This is completely arbitrary and is only used to define a proper default for the value of tau equal to be 1. It's nothing else than that. But the function g now goes into another function f. Sorry for that. But this is very important for applying our algorithm to a variety of surface meshes, especially surface mesh scales. We are determining a characteristic length for each surface mesh, and we say this must be the maximum value of our smooth distance field. But we could also choose other values, such as the length of the given curve, to find a different behavior. And by that one, we're equally scaling the argument and the output value to match the same smoothing, let's say, strength for different surface mesh scales in the end. And now the last part comes in. That's probably the easiest one and the most understandable. As we see, we have now no longer the norm of gradient to be 1, but this is the simplest equation that we can come up with to at least make the norm of the gradient increase linearly with the distance to the initial curve. So with such we can now construct the potential. And let's go a little bit to the implementation. They're only put in a few nodes. There is also no unique implementation, mostly an algorithm based on our smooth operations. But we have provided an implementation based on the heat geodesics method from libigl to build the smooth distance field. And we're really lucky by that one because we get smooth distances as a byproduct by increasing the time step. We don't need those locus points then. Then as a second one, we use the flip-out algorithm from Geometry Central to actually trace the geodesics. And here's the lucky part. We already heard about intrinsic triangulation. Flip-out uses intrinsic triangulation and has intrinsic edge flips to determine those locally shortest geodesics and finishes after a finite number of steps. The cool part is also It's cool. That's the algorithm. It's very cool, sorry. So that's the cool part, sorry. Because we saw earlier, we only need edge length, and that's the same for the flip-out algorithm. You see, we only provide a representation of the edge length, so we calculate those new edge lengths based on our lifting operator, we will never actually represent the lifted surface. It's much easier that way, and Flipboard actually expects such input, so it's also much easier to program this way. As a last step, and we have to include a post-processing step. This is basically due to discretization error. We represent our smoothed distance field as a piecewise linear approximation over all those vertices. And for coarse triangulations near the initial curve, the curvature that we need to actually move the curve around is not really working the way that we want. And actually, we're introducing a lot of noise again, which is actually what we don't want to do. What we do is we're using a small Laplace relaxation that for points that lie on an edge, they will all be kept on this edge. Yeah? They will be slightly moved on that edge to build a smoother curve. This is something the algorithm in this discretization form cannot achieve. So what are our results? We start with the performance, I would say. In all our experiments that we had, we achieved interactive or, let's say, at least near interactive frame rates, depending on the definition of your interactivity. For, let's say, roughly roughly 1 million faces, we have a second of computation time. That's kind of good, I would say. It's hard to tell. And yeah, here's some example of our Grumpy Pumpkin that was computed in, as I remember, something about 200 to 300 milliseconds. Another part is, one could now think that the generation of the potential took much longer than the tracing of geodesics. Actually, is kind of the other way around. Most of the time, the generation of the geodesics took much, much longer, or not much, much longer, but took longer than the generation of the potential. But there is a break-even point. We say we couldn't really measure the break-even point as it only appears for millions of triangles, and we couldn't use it therefore. But for the largest mesh, the fairing model that we have here, we applied the algorithm, and still the tracing of geodesics was a little bit smaller, or it was a little bit slower than the potential construction. But now let's come to the effect of our parameter tau. How does it work? We want to show it at the carotid arterial vessel that can also be used to, for example, cut open blood vessels and whatever. And we're providing this initial curve, and we zoom into the middle part here a little bit. And let's say we start with a value of tau equal to B0. And there's no surprise. By definition, the curve that results must be a locally shortest geodesic, and that's what it is. It is the smoothest curve that we can get from this approach, but it may also be as far away as possible. And if we slowly now increase our tolerance parameter to 0.5 in this case, we see that now the curve follows the original shape a little bit more. We increase even further, and we see it's still more constraining, but we see also that the curve is not as smooth as before, but still smooth. We can do this even further and try to increase the tolerance parameter to make the kind of curve that you would like to have for your initial curve. So now let's talk about the robustness. We have done this in two parts. We've introduced a planar mesh with a sudden change in triangulation degree and showed the smooth curve part for two different tolerance parameters, one for a value of 3, I think, and one for a value of 5. And what we can see here is that the smoothing, of course, is slightly different. This is to be expected, but it is very similar, especially when we're taking a coarser triangulation into account. Then, as I said, the piecewise linear approximation of our smooth distance field, and therefore the piecewise linear approximation of the potential, somehow is less restrictive. So apart from that, we see similar strategies. We have also taken a second part, which, with the Dragon model, we changed it a little bit to have a high tessellation degree on the left side and a low tessellation degree on the right side. And there we can see the following. If we zoom in on left and right side, this is exactly the less stringent behavior on the right side that it was telling, but still, you can somehow argue that it is a similar degree of smoothing for the same parameter for various kind of tessellations. Okay, so last step, we also compared to the hypersurface smoothing of Marco-Livsu, which solves a similar application problem. Here we must say this approach is much more generalizable to even surfaces and somehow tries to relax segmentation boundaries. Here's to say, therefore, if we want to smooth curves, these curves must build boundaries of a bipartition. This is a restriction that is intrinsic to this kind of algorithm. Our algorithm is capable of open and closed curves right now. They don't have to fulfill any kind of special topology, except, which is only based on our implementation, that the curves are not allowed to self-intersect. What we can see here is, in this image at least, and in our measurements, we can say there we actually have a comparable quality. If we go a little bit further into the details, then we also have a complete time increase, so the hypersurface smoothing is 5 to 20 times slower for the meshes we tested. And furthermore, that's our major problem. The result may not be necessarily a curve. This is also intrinsic to the nature of the hypersurface smoothing, as it represents its smooth curves as a level set of a smooth scalar field. It, of course, must happen. The level set of a smooth scalar field must not again be a closed curve. And if we need a closed curve, this might be a not unstable case for some cases. Another part that we somehow saw, to be honest, with the cow model, I wasn't really aware of that at first, was that we see stronger bias based on surface triangulation. If the triangles are a little bit stretched, then you see that the approach, the hypersurface smoothing approach, leads to a little bit more bias here. But we also have to say, as I was saying, post-processing, let's look at our algorithm for coarse triangulation when there is no post-processing available. And actually, it's a little bit devastating at the start. I was really unhappy with this. We can see our blue line, also compared with hypersurface smoothing again, provides these jaggy things again. And these are exactly the things that we wanted to get rid of. But this is also really deeply connected to the point that we approximate the potential with a piecewise linear function. And here, the algorithm cannot act any longer. Even though the math turns out to be right, the algorithm cannot act here. And so we said we wanted to introduce an edge relaxation. All points keep to be on the same edges and the same vertices, nothing changes, only their weights are changed slightly with the Laplace relaxation. And we see this is the resulting curve from applying, in this case, 4 Laplace relaxations. So, and to be honest, this doesn't introduce any kind of performance overhead. In all cases, it took less than 1% of our overall running time. So that it is, again, comparable. So to the conclusions, I think, yeah, we somehow provided a simple algorithm with an interactive performance, but the problem is that with its simplicity, we also got its major limitations. We are tracing geodesics, and the problem is the curves will always be shortened because we want to trace locally shortest geodesics. We're not capable of enlarging a curve, and some curve smoothing may actually require the enlarging of a curve. Also, it was turned out that we do not actually control the Hausdorff distance, and that is true. This is also intrinsic to our optimization problem and to the kind of way how we formulate the thing. We cannot really address this with the idea to lifting it and tracing the geodesics. We can only hope for it to be somehow okay. It's an approximation in this kind of sense. But these are the limitations of the algorithm. The limitations of our implementation, as I was already stating, are, for example, the noise factor that we've seen from the disabling of the post-processing, and are that curves are not able to self-intersect, which is mainly a part of the flip-out algorithm. We would choose another tracing algorithm, then curves might also be self-intersect. Nothing would actually be a problem with that. And our future work, therefore, also would include the search for alternative potentials to apply for an even better smoothing approach, and the use of submeshes. We could, of course, leverage the intrinsic triangulations, but before we could do this, we could also use a submesh around the initial curve to also bound the maximum distance, so that's such the curve is not able to move as much apart as possible. This would also, of course, improve the performance of the geodesics and heat method. A last point would be to include fixed constraints, and I think this is the hardest part. As we're using our relaxation process, providing certain constraints like differentiability, and somehow these things gets harder and harder. We would need to get back to an integral approach for that, and yeah, that would be also future work. And with that, thank you very much for your attention. You can find the code here, but I have to say it's not polished, and it will be polished during the course of the next weeks. And you can visit us, and I'm grateful to be here.
Any questions from the audience?
Hey, nice talk. Just one question. Since you're using flip out, it seems like another natural way to smooth a curve would just be run some flip out iterations, but don't go all the way to a geodesic. I mean, because it's just like curve shortening flow. Did you try this as well?
Yeah, I tried this. And I was hoping that it worked at the start. But the problem is that flip out always tries to evenly smooth out the curve and tries not to follow the original shape. Therefore, if you have, for example, a curve that goes like this, flip out will try to make it a circle around the original shape. And that's more or less the problem. You cannot really control the way that flip out is doing that.
Gotcha. Thank you.
So I'm trying to understand your method a little bit, and the way I'm going to do that is get away from surfaces and go to the Euclidean plane. So if you take the Euclidean plane and you subtract a square, and you connect a curve with the two endpoints there, right, which are the two edges of the square. It seems like in your case, you would actually reproduce that exact geodesic, because that is a geodesic in this space, in that case, right? It's the shortest path between these 2 points. And so you say you're smoothing the curve, and I'm trying to understand what does it mean to smooth the curve, because it feels more like an interpolation between the geodesic and whatever curve you've specified, regardless of what the smoothness of the curve is, right?
Yeah, that's more or less true. The problem with the smoothing that we have is there is no, apart from the mathematical definition of smooth, let's go away from that, there is only a vague definition of it. And we said we want to reduce geodesic curvature. And the question is then in which kind of sense we want to reduce the geodesic curvature. The optimization approach that we use, that because we have an integral on the integral energy, reduces the geodesic curvature in an average way, and not in a uniform way or in the supremum's norm way. And therefore, your interpretation is totally not wrong. You can totally see it like an interpolation between a geodesic and the initially given curve, such that you would somehow in between get another version that is a little bit smoother but still follows the original a little bit.
Thank you for the talk. I have two questions. So the first one is, I don't think you said this explicitly, or maybe I missed it, but the variational problem that you wrote down, is it identical to just measuring geodesic distance, or sorry, length or energy of the curve on this lifted space?
Yeah, that's
okay.
Yeah, that's exactly. If you take this step, so I can also go back.
Sure.
To the, you mean this one? If we go back to step number 3, then we actually formulate this one in the optimization problem. And this is exactly measuring the length of the curve in the lifted surface. And if you put in all the other stuff, there's the lifting operator, and then there's the other curve, then you exactly get the following formulation. It directly follows from this measuring of length in the lifted surface.
Okay, and then second thing is that in the construction of your potential, I think you explicitly forced it to be scale invariant by dividing by the maximum distance, right?
Exactly.
But how do you sort of control smoothing at different scales? So does your parameter tau control how much you smooth out, small features versus larger features, or is it unrelated to that?
That is a really good question. It is, we do not control for that. We have a uniform parameter for the overall mesh, and if you have, say, a really long curve, then by definition of this approach, the small features will get smoothed out. We will assume for longer curves or for larger meshes that these features are not, in this case, are not wanted. But you're true, if we change the characteristic length and try not to use only one characteristic length, maybe we use a length field, then we could probably change this kind of behavior and could say, okay, specific local features that we want to keep, we could keep then.
Okay, thank you.
Okay, thank you.
And thank you for the talk. If you're always contracting the curve, did you consider a way to then like afterwards reinflate it to get something more, on average, the same length?
Yeah, I tried this a little bit, but it was devastating results, I can say. Yeah.
Okay.
In other words, I tried before, but then we have no convergence anymore when I wanted to do this. I can do this on some meshes when they're really good, then in some sense you can try to enlarge it again, but you never know. If you're on a sphere sometimes, or much worse meshes, you can always receive not really a convergence. And we wanted to have an algorithm that finished after a finite number of steps, so we didn't look into this direction anymore.
Okay, thank you.
Hi. If you have an input curve that has, sort of a loop in it, not in the sense of self-intersection, but, the curve comes close to itself, moves further apart, comes closer again, it seems to me that the finding of the geodesic could, for certain values of tau, choose to cut off that entire loop.
That is totally true. Yeah.
And what the behavior that would lead to is that the curve you get as a function of tau does not vary continuously. Is that indeed the behavior that you observe?
Yeah, that we observed, exactly. I can show with the, you may be able to see it with the brain model here. There we tried to draw such curves for a high resolution mesh. And yeah, we had to restrict the curve a little bit more, as you see here. We already cutting up a few parts in here. And by reducing the tolerance parameter a little bit too much, we will totally cut them out, and they will not be there anymore. That's the problem with the Hausdorff distance. I think so. We are not really forced to follow the original curve too closely in this kind of regard. Yeah.
All right, thanks. And this actually seems related to some work that people have done on curve simplification that where that property actually is desired, where they are trying to remove entire parts of the curve and arguing that that is a form of abstraction. So I find that connection very interesting.
Oh, thank you very much. I didn't know about that.
Hello, I have two questions. One is I have used snake method. You have mentioned it in your paper. Have you compared with the snake method in your results? This is my first question. My second is, can your method guarantee no collision during the iteration?
So if I do understand whether we compare to the snake approach?
Yeah.
We have considered the snake approach, but the snake approach is used for feature detection, if I'm not wrong with that. And we try to smooth the curve in the absence of features. So we, at that point, it did not seem to be necessary to compare against snakes. And no, we didn't compare against snakes directly. And to the second part, can you repeat the question, sorry?
Yeah, okay. My second is, can you guarantee no collision, no self-collision? Self-collision during
No, yeah, we can. Especially the algorithm, our algorithm does not guarantee that. As we're tracing the geodesics with the flip-out algorithm, it's a guarantee of the flip-out algorithm in this case. Because the flip-out algorithm guarantees that we will find a curve in the same isotropy class without self-intersections, without crossings. So there will never be a crossing when we determine it.
Okay, thank you.
I have a simple question. So you reduce smoothing problem into a geodesic problem.
Exactly.
How do you do closed loops? Like, what's the start point and end point for?
That's a good question. For closed loops, we have no start and end points. The problem is, as you see in the optimization formula, we actually have these problems. You might think of that we might be able to construct a closed loop that will always run perpendicular to the gradient of phi, so it does not really need to be constrained. There are indeed these strange cases, but they are rare. They actually did not really happen in practice. They are totally unstable. A slight change of the potential would totally erase that. The flip-out algorithm is a local optimization routine. So we will, of course, keep everything variable. So every point can move in this kind of direction. But as we are locally optimizing it, we will try to follow the curve along the given potential still. So it's still the algorithm itself that shrinks the loop in the end.
All right, if no more questions, let's thank the speaker again.
Okay, thank you.
So next we have reconstructing curves from sparse samples on Riemannian manifold. So the speaker is Marin.
Hello everyone, and thank you for the introduction, and thank you all for being here for our presentation. I will be telling you today about our work on reconstructing curves from sparse samples on Riemannian manifolds. But we will start by talking about cats. Well, at least provided that you can see the shape of a cat in that set of sparse disconnected points. This is the problem of 2D planar reconstruction, and we have a lot of methods that are already able to deal with this problem, and we get a lot of inspiration from the way our brain functions, because we are pretty good at telling the shape of that point, that set of disconnected samples. Now, the problem appears when our samples do not exist on the plane anymore, but they live on a surface. They live on a manifold, and we will use throughout the presentation curves on surfaces because they are easier to visualize and to imagine and to understand what's happening over there. So now, how do we solve the problem of curve reconstruction? Because a lot of the assumptions and guarantees that we have in the planar case do not hold anymore. So first, let's see how others have solved this problem. And to the best of our knowledge, there is only one work that deals with curve reconstruction in Riemannian manifolds. And their method is relatively simple. They just compute a minimum spanning tree of the samples, and they swap the Euclidean distance that would be usually used in the plane for the geodesic distance on the surface. Now, their contribution also comes with the sampling condition, and if the samples satisfy the sampling condition, the minimum spanning tree is guaranteed to contain the actual original curve. However, they require very, very dense samples on the surface. So that is a problem, and I will further introduce some methods that work with curve reconstruction in the planar case to drive some, to get some inspiration from there. As we've seen before, we have in both curve and surface reconstruction from point clouds two main categories of methods, the implicit methods and the explicit ones. The implicit ones compute some type of indicator function or sign distance function that tell us the difference between the inside and the outside, and then by taking the level set of this function, we obtain the curve. These are interpolatory methods, so they do not pass through the samples that we have. However, I will focus a bit more on explicit methods because this is what we wanted to extend to manifolds. And this has been a highly researched topic in the past decades. We started from crust in '98, but we still have some publications even in recent years. And what they usually do is they start by computing a graph on the input samples, and then they extract a subset of the edges from this initial input graph. The Lawonn triangulation is a really good choice for this initial graph because it has a lot of nice geometrical and proximity properties. But what I will do is I will go into a bit more detail about this last method, SIGDD2D, because they offer some really, the most relaxed sampling conditions in the plane, and they also have the best results for closed manifold curves. So as I've said before, these methods usually start from an initial graph. In this case, their initial graph is called SIGDT, which is the intersection between the spheres of influence graph and the Lawonn triangulation. Now, don't worry about the spheres of influence graph. I will tell you more about that a bit later. But we just have this initial boundary, and we can see that part of the graph is just squished together, and we want to fix that. And how did they do this in the initial method is to look at the triangles in the Lawonn triangulation, find these non-manifold vertices where the boundary is squished, and try to add triangles back to the shape such that all of the samples are either on the boundary or inside of the boundary. Now we can see that there's one little vertex that is still inside of the boundary, and we would like all of them to be on the boundary to create a full reconstruction of our samples. So in that case, they do something similar to the opposite of the inflate operation, which is sculpt. We look at the triangles that are inside of our shape and carve away some of them to expose all of the points to the boundary. Now, I've told you before that they have the most relaxed sampling conditions for this initial graph, SIGDT, and I will go into a bit more detail about that. And most of the sampling conditions in the realm of curve reconstruction relate to the medial axis. And for the curve here, in red, with the black samples that are just all around it, we can compute the medial axis, which is the collection of points that have minimal distance to at least 2 different points on the curve, or you can also imagine it as the collection of centers of spheres or circles, of maximal circles that can live inside of the curve. Now, for any point on our curve that is not necessarily a sample, x in our case, we can do 2 things. We can compute the distance to the nearest sample, d, and we can also compute the distance to the medial axis, and that is called the local feature size. And one of the first sampling conditions that has been introduced in the seminal crust paper by Amenta and colleagues was called epsilon sampling. And for epsilon sampling, what they did was to bound this ratio between the distance to the nearest sample and the local feature size by some epsilon. And they can guarantee that their reconstruction contains the original curve ordering under some epsilon conditions. There was also an improvement in terms of theoretical guarantees, which was instead of taking the local feature size of one single sample, we considered the interval of samples that bounds our x here, and we take the minimum local feature size on that interval instead of just of one single sample. This is called the reach sampling, and is usually defined by rho. And in the SIGDT method, this is what they use to define their sampling condition. Now, everything is nice and pretty in the planar case. Now we wanted to move to manifolds. And we have here 2 examples of surfaces, like the witch hat and the tube. We can imagine that the tube here is hollow. It doesn't have an inside. And we want to see what happens to the medial axis in cases like this. So we have our 2 curves, as before, defined on the surfaces now. And let's try to find the medial axis. Well, for the witch hat, there is only one point that is the medial axis. Only the point on the top of the surface is actually the one that has minimal distance to 2 different points equal. While for the tubular shape, there is absolutely no medial axis if we don't have an inside. So we already run into problems. We cannot define a sampling condition that is purely based on the local feature size if we do not have a good control over our meshes. Let's try to furthermore compute the local feature size and see how that goes in these conditions. So we have our point on the curve P. We can, of course, compute the distance to the local feature size. But that distance to the local feature size is greater than the entirety of the curve. So we can find, if we travel along the curve in one direction or another, we can fully encompass the curve without ever reaching the medial axis, which is a problem since now the values that we have for a local feature size are too large to be leveraged for a sampling condition. Now, we go back to the other method that managed to reconstruct curves on Riemannian manifolds. And what they did was to use some information from differential geometry. So what we want to do is we really liked how our methods worked in the planar case. So we want to work in some specific area where our surfaces act kind of like a plane. This is called the injectivity radius, and we can see that we can map from the Euclidean plane to the surface without overlaps. And this is what allows us to lift our sampling conditions to surfaces. Just as a reminder, I promised you some theoretical guarantees in the planar method. And what they could prove is that for raw sampling, with rho less than 1 and u less than 2. U is just a non-uniformity ratio, so they allowed for non-uniform sampling. That's just the ratio between two consecutive edges, but what's important for us is that we can have non-uniform sampling. They proved that this sigDT graph contains the reconstruction. Now, this is the reconstructing curves on Riemannian manifolds paper. They also proved that for a uniform sampling of the curve with distance bounded by the injectivity radius of the entire manifold, the minimum spanning tree contains the reconstruction. And what we wanted to do is to use these two parts. We want to have the sampling that is bound by the local feature size, so we care about how our curve looks, and we want to keep features that are important. We want to allow non-uniform sampling because that's more relaxed and we would not like to impose something like that. But we need to use the injectivity radius to be able to move onto surfaces. So what we managed to prove in our paper is that if a curve is sampled with rho less than 1 and non-uniformity ratio less than 2, our initial proximity graph contains the reconstruction, the original reconstruction. What we had to do in order to achieve this was to modify the reach sampling, the interval sampling condition, to now not only take into account the local feature size along the interval, but also the injectivity radius along the interval. So we managed to obtain and prove a sampling condition that works on surfaces, and it's also more local and more sparse than the state of the art. However, that's a lot of information, so what's important here is that state of the art could only reconstruct curves that are sampled like the blue version here, which are very dense, and basically every edge has to be sampled for the method to be able to reconstruct, while we are able to reconstruct samples like the purple version, where we allow for non-uniformity and also for fewer samples in total. I promised you some more information about the spheres of influence graph. This will help us define our initial proximity approximation. And the spheres of influence graph has been introduced into SANT in 1998 as a proximity graph, as a clustering graph. And the condition is pretty simple. We connect two vertices in this graph if the distance between them is less than the distance to the sum of the distances to their nearest neighbors. However, another explanation of this definition, a more visual one, and that one that also gives us the name for this graph, is that we center a circle or a sphere at each of the samples, and then we start growing it outwards until we touch another sample. We stop there, and then we connect all of the points whose samples intersect. This is equivalent to the initial nearest neighbor definition, but it helps us to get more intuition about what this graph does in the background. So what we wanted to do is to gain this knowledge, to use this knowledge from the planar case to emulate the sigDT to the method. So of course we start from some samples on a surface. Since the spheres of influence graph is only defined in terms of distances, there is absolutely no issue in us just computing the spheres of influence graph by replacing the Euclidean distance with a geodesic distance. So we can just compute the spheres of influence graph. But now, as it was mentioned before, in the plane we have this very nice duality between the Voronoi partitioning, the Voronoi partitioning and the Lawonn triangulation. And this, unfortunately, does not hold once we start computing the Voronoi partitioning on manifolds. And fortunately, the theory was on our side, so we didn't have to go all the way to the Lawonn triangulation, so we just stopped at computing the dual of the Voronoi graph. And how we do that is we add each sample one at a time, and then we go through all of the vertices, marking which sample is the closest to each of the vertices in our mesh. So we can see now that the mesh is split into two. We have the samples that are closest to we have the vertices that are closest to the sample on the paw, and the ones that are closer to the back leg. And we continue doing this until we have added all of the samples of our input. And once we have that, again, since we do not need to go all the way to the Lawonn triangulation, we just connect the samples where the Voronoi partitions touch each other. So we have obtained the spheres of influence graph, and we have also obtained the dual of the Voronoi partitioning. In the original method, they just intersected these two by keeping edges that were both in the spheres of influence graph and in the Lawonn triangulation, dual Voronoi in our case. So we do the exact same procedure, and we obtain this graph. This was, however, only the first part that I've mentioned from the original planar method. And just as a quick reminder, they used this just as an initial approximation. And then they added triangles such that all of the samples are inside, and then they removed such that all of the samples are on the boundary. Now, there are some important concepts that we're missing here, unfortunately. What's the inside and what's the outside of something that lives on a surface? We cannot define that. And since we abandoned going all the way to the Lawonn triangulation, we do not have triangles that we can use to inflate and sculpt our shape. So what we did was to take a step back, realize that we are working with a graph, and we want to extract a cycle. So we just leverage the traveling salesman problem to extract a cycle of our samples. We use, once again, a minimum spanning tree, just like the original method on Riemannian manifolds. And we do some edge swaps to minimize the total length of the curve. And we do these edge swaps. We try to minimize the total length of the curve because in the 2D curve reconstruction, this seemed to be a really good heuristic about approximating a curve that matches what our visual systems want to see. So we wanted to extend that to manifolds as well. Now, we have proposed a method that has theoretical guarantees and is also able to work on surfaces. Let's investigate some applications for why we would need curves on surfaces or curves on manifolds. And one of the first examples that we came up with was to extract designs or patterns from various artifacts, like cultural heritage artifacts, where somebody would just extract samples that live on the boundary of a shape, and they would be interested in maybe analyzing the final shape of this point set to gain some more information about the scans. By using these samples, the state-of-the-art in curve reconstruction manifolds that I will just call MST method from now, did not manage to obtain a good result. So we can see that there's only one curve connecting basically all of the samples, while ours correctly managed to separate these two shapes and also reconstruct the actual outline of the shape. One of the applications that was used in the state-of-the-art in curve reconstruction on manifolds was to try to reconstruct motion curves in the space of rigid motions. And that is the Cartesian product between the rotation group SO3 and R3. And for their method, for a curve just like this one, they require 21 samples to be able to correctly reconstruct the original trajectory, while our method only requires 9 samples. So we are able to reconstruct the original curve even with less than half the samples. And this is particularly difficult for areas where the different parts of the curves are very close to each other, but our method still managed to connect them in the original order. One other idea that we had was to try to use this for sparse data visualization. For example, here, the texture of the Earth is computed by using the temperature measured on 30th of March, if I'm not mistaken, everywhere on Earth with a high accuracy. And we just extracted a bunch of samples, around 40 samples of this data set, such that we don't have to use the entire huge data set. to try to extract the isoline that would connect similar temperatures on the globe, to extract some more information about maybe temperature patterns, or if we want to use other parameters from this type of meteorological data. And once again, the state of the art in this regard did not manage to reconstruct the curve, and even though we have some wide areas in which some areas in which we don't have a lot of samples, just like here, our method still managed to obtain the original curve, as it can be seen by the coloring of the sphere. Now, since we talked about contours and isolines, we wanted to also explore another type of contour application. And this was related to contour matching improvements, where we tried to match a 2D shape with a 3D human shape in this case. This would be the ground truth that makes sense for the outline of the human shape. And we just used another method that already had good results in this regard, elastic 2D, 3D. And we sampled about 3% of their points on the human body, and we wanted to reconstruct the ordering of these samples to try to improve the matching between the ground truth and our reconstructed ordering. And we can see that in the areas like the neck around here, because we changed the ordering of the ground truth samples, we obtained because we changed the ordering of the elastic 2D, 3D samples, we obtained an ordering and a contour matching that is more similar to the ground truth. We already have some theoretical guarantees for our method and a bunch of applications, but in terms of future works, we are thinking about trying to find a graph that has better theoretical guarantees, maybe by leveraging some properties that are intrinsic to manifolds, not only trying to lift methods from the planar case. And right now, we are only able to deal with closed manifold curves. So it would be very interesting to try to experiment with open curves, with non-manifold curves where we have intersections, and we are able right now to reconstruct multiple curves because we are using a clustering algorithm in the shape of the spheres of influence graph. But this is just left as a choice for the user. We do not have any theoretical bounds on whether we are able or not to reconstruct these multiple curves, and we would like to investigate more in that direction. With all of this, if you want to have access to our code base, you have the QR link here. I'm happy to take any questions, and thank you very much for your attention.
Thanks for the talk. So most of your discussion and examples were on two-dimensional surfaces, but SE3 is higher dimensional, right?
Yes.
Does anything in the algorithm change in that case, or is everything just exactly the same?
Nothing in the algorithm changes, but we had to do some changes in how we encode that motion, just to make sense for our Voronoi partitioning. I will refer you to the paper for that, because we also have a proof on how to move from R12 to R9, just to make it easier for our algorithm to deal with that. But no, the algorithm still stays the same. As long as you can compute distances, you can compute the Voronoi partitioning and the spheres of influence graph, and you can apply the method.
Thanks. And one more quick question. So in these examples, all the results look a little bit polygonal, because you're just connecting these points. If I wanted to do some sort of Bezier curves on surfaces, would that be like simple to add at the end, or do you think that would be a whole new project that you'd have to do differently?
We do not, so we only output the ordering, the final ordering of the samples. We do not deal with how the curves actually look. In this case, we actually used flip out to make the curves nicer for visualization purposes. But transforming them into Bezier curves that would actually pass through the samples would be another work already.
Thanks.
Thank you for the talk. So you mentioned that you have to bound things by the injectivity radius. but I didn't catch, do you have to actually compute the injectivity radius for every edge in your graph? And for every, for each vertex of that edge?
We do not have to compute that in our method, but if the samples are chosen such that our conditions hold, we are guaranteed to obtain the correct result.
I
So
see.
we do not have to compute it in our method, but that is the condition under which we can guarantee to have the correct reconstruction.
Okay, thank you.
Hi. Very nice work, by the way. I have a question about first of all, the slide you have with the aircraft path. Yeah, that one. Was that meant to be in free space, and then someone gives you the sparse samples plus direction, or is it just the points?
You have the points and the rotations.
Okay, right. Okay,
Yeah.
cool.
That's what I was saying, like here. This is a very critical case, let's say, because you have spatial proximity, but the rotations are very, very different. So that's also why we need the state-of-the-art method needs way more samples than that. So yeah, we have the position and the rotation as input.
Okay, excellent. Another one is, I know in the slide with the future work you mentioned non-manifold cases. Should I understand it as like, if someone made samples where it kind of obviously make like a cross, like an X,
Mm-hmm.
that's what that meant,
Yeah,
right?
exactly.
Okay.
Yeah, like self-intersections.
Cool.
Yeah.
How hard is it do you predict that would be?
What I would say is that not even in the 2D case, there are not a lot of work that can deal with non-manifold curves, because the focus has been put on the manifold, closed, very nice curves. Yeah, I think it would be difficult, because we lose a lot of these assumptions that we have, or yeah, it's difficult because you never know whether there will be a whole or just some sparser samples. Yeah, it's a difficult problem to solve, especially in this type of domain.
Okay, thank you.
Thank you.
I have a follow-up about this airplane example. How did you build the manifold? You said something about R9, but you have rigid body motion, so this is Studi quadric in 7-dimensional projective space.
So we started initially from R12 with the rotation matrix, R9, and the 3 more coordinates for a space, for the position.
But these are not independent, right? You have orthonormal matrix, so there must be some products equal to 0 or 1. You have, yeah?
Yes, but I do not remember the name of the theorem right now. I'm very sorry, and we can take this offline. But there are some results which guarantee that our Voronoi partitioning in this higher dimensional space can be reduced to R9. And in that, we can just compute our Voronoi partitioning and obtain the results that we have here.
Okay, we can discuss it offline, but to me still R9 is too much. Yeah? But anyway, yeah, thank you.
For the planar case, we know that the epsilon sampling guarantees reconstruction, but in practice we find that much looser conditions are sufficient. So have you made similar observations here? So what works in practice, but you can't prove it?
I see. Well, one prime example is this one, which we have way sparser samples than what our conditions would require. But unfortunately, we don't have like quantitative results in that direction. We are planning to have like an entire benchmark, maybe use some segmentations results, as we've seen before, that as a case of curves that naturally live on surfaces, but no, we do not have actual results in that direction.
I was curious, how do you check the injectivity, your sampling rate satisfy the criteria, in particular injectivity radius criteria, in particular when your manifold is higher dimensional?
I see. The only example in which we checked our, the only example in which we actually checked our conditions was this one, and we just used the distance to the cut locus as a distance for the injectivity radius. For anything that lives in higher dimensions, we did not check the conditions. We just obtained the results experimentally by using samples and seeing how they act.
Okay, so you compute the cut locus explicitly?
Yes.
Okay.
Yeah.
Cool.
But only to generate this data set. Like in the algorithm, we do not need to compute this. We just, yeah.
All right, thank you. Yeah, let's thank the speakers one more time. Thank you, guys.